Have you ever shuffled across a carpeted room in your socks, casually reached for a metal doorknob, and zap? You get a sudden, totally unexpected shock. We've all been there, right? Well, that tiny spark is actually a brief, everyday encounter with literally one of the most fundamental and powerful forces in the universe. Welcome to today's explainer, where we're going to make the invisible visible. We are looking at the unseen reality of static electricity. You know, what it is, where it comes from, and exactly why it happens.
So here is a quick look at our roadmap for today. We'll start small with Meet the Atom, move on to the rules of charge, then check out charging by friction and charging by induction before zooming all the way out to measuring the force. Let's get right to it.
Section 1. Meet the Atom.
To truly grasp static electricity, we kind of need to set up the cast of characters first. Inside everything you can see and touch, including you by the way, are atoms. And these atoms are composed of just three main subatomic particles. We have electrons, which carry a negative charge, we have protons with a positive charge, and we have neutrons, which are completely uncharged, or, neutral. This trio right here, it's the absolute fundamental recipe for all the electricity we experience every single day.
Now, what's really interesting about this slide is how these particles are actually arranged. See that super tight cluster right in the center? That's the dense core, called the nucleus, and it contains all those positively charged protons and the neutral neutrons. Because of the protons, the nucleus itself is positively charged overall. But look at the outside. Those negative electrons are hovering, just kind of zipping around in orbit around the center, held within the atom by the attractive electric forces from that positive nucleus. They're hanging out on the outer edges, which makes them incredibly important for our next point.
Look closely at the mass difference in this table. A proton has a mass of roughly 1.67 times 10 to the negative 27 kilograms. Sounds tiny, right? But an electron? It's much, much lighter, about 9.12 times 10 to the negative 31 kilograms. To put that into perspective, protons are massively heavy compared to electrons. It's literally like comparing a bowling ball to a marble. And this crazy weight difference explains exactly why electrons are the ones that get moved around so easily. The heavy protons stay firmly put in that dense nucleus, while the lightweight electrons on the outside are basically free to be bumped, rubbed, or pulled away.
Section 2. The rules of charge.
Okay, so we've got these lightweight negative electrons and heavy positive protons. The golden rule governing how these tiny particles interact is beautifully, almost surprisingly simple. Like charges repel each other, and opposite charges attract. That's the whole shebang. If you put two positive protons together, they actively push away from each other. Two negative electrons? Yep, they push away too. But bring a positive proton and a negative electron near each other, and they are powerfully drawn together. Opposites attract.
And this rule isn't just some modern physics discovery. People have been observing it for literally thousands of years. As the source text notes, ancient observers found that amber, when rubbed with wool, attracted other objects and was said to be electrified. Fun fact, the Greek word for amber is actually electron, which is exactly where we get the word electricity. So if you've ever rubbed a balloon on your hair and stuck it to a wall, you've replicated this exact ancient experiment. You've personally witnessed the invisible pull of static electricity.
Section 3. Charging by friction.
So how exactly does the balloon, or the amber for that matter, get charged in the first place? Well, when you rub two materials together, like your socks and a carpet, you are actively adding energy through friction. This physical rubbing literally tears those loose, lightweight outer electrons right off the atoms of one surface and dumps them onto the other. The material that gains the electrons becomes negatively charged, obviously, and the material that loses them is left with more protons than electrons, making it positively charged. This whole process of gaining or losing electrons, that's called ionization.
So the crucial point is that this transfer of electrons happens in exact, whole numbers. This is a concept physicists call quantization. You absolutely cannot transfer half an electron. It's impossible. Charge always moves in whole, measurable packages. The total charge of any object is really just the number of extra or missing electrons multiplied by the basic charge of a single electron. It's just incredibly precise.
Section 4. Charging by induction. Now, friction makes total sense because things are physically touching. But let's move to and see how this builds, because the physics gets even more fascinating when we look at charging without any contact whatsoever. Imagine bringing a highly negatively charged rod near but carefully not touching a neutral piece of plastic. Because we know, likes repel, the massive negative charge on the rod actually shoves the plastic's own electrons slightly away from the surface. This leaves the surface of the plastic slightly positive. We call this polarization. It's wild. The rod has induced a positive surface charge without ever making contact. To see a permanent version of this trick, Notice what happens when we bring a negative rod close to a neutral metal sphere. The sphere's outer electrons are strongly repelled to the far side. Now, if we attach a grounding wire to that far side, we give those fleeing electrons an escape route right down into the Earth. Once those electrons drain away, we cut the wire and then remove the rod. The sphere is now permanently missing those electrons, leaving it with a strong positive charge. It's basically a magic trick, but it's pure induction.
Section 5. Measuring the force. Now, physicists don't just sit around observing these pushes and pulls, they actually mathematically predict them, and this brilliantly illustrates how. Notice the force vectors, or basically the arrows between these particles. In the top pairing, a positive and negative charge have arrows pointing inward. They are strongly pulling towards each other. In the bottom pairing, two positives have vectors pushing away in opposite directions. The length of these arrows visually represents the physical force, but how do we know exactly how strong that force is in real life?
Well, that brings us to Coulomb's law. Now, don't let the technical phrasing intimidate you here. It's quite simple in plain English. The law essentially states that the force between two objects depends on two main things. First, the size of the charges. The bigger the charge, the stronger the pull, or the bigger the shock you get. Second, the distance between them. The closer the objects are, the massively stronger the force becomes. Actually, inversely proportional just means as the distance shrinks, the force absolutely rockets upward. That's exactly why your finger doesn't get shocked from across the living room, but the very second it's a millimeter away from the doorknob, zap. So, we've journeyed all the way from the tiny orbiting electron to the fundamental mathematical laws that govern how everything in the universe pushes and pulls on everything else. Static electricity, it isn't just a pesky annoyance on a dry winter day, it's a very visible reminder of the foundational forces keeping matter itself intact. And it really makes you wonder, if these massive invisible forces are holding our very atoms together in total silence right now, what other unseen connections are we interacting with every single day without even realizing it? Thank you so much for exploring the invisible with me today in this explainer. Keep asking questions and always keep looking deeper.